In this video, we look at the combined rotational and vibrational energy levels and transitions in a diatomic molecule. When we modeled the rotational behavior of a diatomic molecule, we neglected vibration. And when we treated vibrations, we neglected that the molecule can rotate. Here, let's combine the two. The diatomic molecule has 3 degrees of freedom, and its states are going to be described by 3 quantum numbers. The vibrational degree of freedom is the displacement, x, and the associated quantum number is n, which can have values from 0, 1, 2, and so on. The 2 rotational degrees of freedom are theta and phi, with the associated quantum numbers j equals 0, 1, 2, and so on, and m equals negative j all the way up to positive j. Since rotation and vibration are essentially independent, we can add the vibrational and rotational Hamiltonians, and therefore we can also add the 2 energies. The overall energy of a combined rotation-vibration state is therefore given by the following. E of njm equals h bar omega times n plus 1/2 plus h bar squared over 2I times j plus 1. Here, omega is the oscillator frequency and I is the moment of inertia. The overall wave function is a product of the vibrational and rotational wave functions. So, psi njm of x, theta, and phi equals psi of n of x, that's a vibrational function, times y jm of theta and phi, that's a rotational wave function. Let's plot the energy level diagram. The vibrational ground state has n equals 0 and an energy of 1/2 h bar omega. The next vibrational state is at 3/2 h bar omega and has an n equal to 1. Now we add rotational energies to this. Vibrational energy level spacings are on the order of 1,000 inverse centimeters. Rotational constants are on the order of 1 to 10 inverse centimeters, so the spacings are much smaller. For each vibrational state, we get a set of rotational levels with increasing spacing. With the j quantum numbers 0, 1, 2, 3, and so on. And again, 0, 1, 2, 3, 4, and so on. Any label with j larger than 0 contains multiple degenerate states. In order for a photon to induce an allowed transition between 2 states, both vibrational and rotational selection rules must be satisfied simultaneously. Specifically, first, the photon energy must match an energy gap. E photon equals delta E. Second, the molecule must have an electric dipole moment, mu not equals 0. And the dipole moment must change as a function of displacement, d mu dx not equals 0. Third, the only allowed changes in quantum numbers are delta J equals plus minus 1 and delta n equals plus minus 1. Let's draw the allowed transitions out of the vibrational ground state manifold up to states with n equals 1. From the 0, 0 state, the molecule can transition into a 1, 1 state. 0, 0 to 1, 1. Both delta n and delta j are equal to positive 1. For the transition from 0, 0 to 1, 0, delta j is 0. Therefore, this transition is forbidden and does not occur. From the 0, 1 state, the next one up, there are 2 allowed transitions. One up to 1, 0, where delta n is plus 1 and delta j equals negative 1, and the other one goes from 0, 1 up to 1, 2, where delta j equals positive 1. This continues for the other rotational levels. We end up with one group of transitions with delta J equals -1, and another group with delta J is +1. These groups are called branches and are labeled with letters. For delta J equals -1, it's a P branch. For 0, it's the Q branch. For +1, it's the R branch. Even though the Q branch is forbidden in our case of linear diatomics, it is possible for more complicated molecules. In summary, we have combined rotation and vibration for a diatomic molecule. The energies simply add. And for transitions, the two selection rules have to be satisfied simultaneously.